Hey everyone, welcome back. In this lesson, we're going to talk about something that might look a little bit scary, a little bit intimidating at first, but know that this is not something that I'm going to expect you guys to understand completely. I'm just trying to get you guys to sort of get a feel for um, some new stuff without necessarily being able to use it, the same way that somebody like myself might use them on a regular basis. But I just want you to see what this stuff looks like before we go on to the rest of the unit. Now, it's not going to be super important to the rest of the unit because I'm going to try to steer clear of the complicated math. But I do want you guys to see at least a little bit of this before we go on. So in this lesson, we're going to be talking about vector quantities, and this might be something that you've heard of before. For any of you that have watched Despicable Me, you'll be familiar with at least the word, and you might remember what it means. But we're basically going to review, I say review for those of you that have watched Despicable Me, and we're going to start from scratch for everyone that hasn't. So there are lots and lots of different things that are vectors or vector quantities, and a couple of the big ones that we use in physics are velocity and acceleration. Now there are more, and we're going to talk about, I think we're talking about just three in this one, but these are two of the sort of big ones that if you opened up a physics textbook, chances are you'll see these two all over the place. So let's begin with trying to understand what a vector actually is. So I'm going to say this basically the same way that it was said in Despicable Me, which is that vector is a mathematical quantity that has both a magnitude and a direction. So magnitude is just a fancy word for size, basically. Now, because we're talking in terms of math, I'm not talking about a physical size like something that's really big versus something that's really small. I'm talking about size in a numerical kind of sense. So like large numbers versus small numbers. So if you had, so if we don't talk about, if we don't go into the complete detail, if you just look at regular numbers. So if you look down here at this point, just regular numbers, they don't have any direction attached to them. Those are called scalars. So if you're just looking at a regular number like 3 is an example of a scalar. And if you look at another regular number, another scalar like 12 is bigger than 3, right? They're both scalars, but 12 is bigger than 3, so 12 has a larger magnitude. Number-wise, it's bigger. So that's the magnitude part of what a vector is. So it's a mathematical object, so we'll probably describe it using numbers, but there's also a direction attached to it, and that's what makes it different from normal numbers. So I could say that a number that doesn't have direction is a scalar. Now it can have units, and by units I mean things like meters, things like seconds, degrees, whatever, hours, Kelvin, whatever. So you could have units attached to a number. So for example, if I say, well, right now it's here, it's about where I am, it's about minus 10 degrees Celsius. So this part right, hang on, this part right here is the unit. This unit is attached to the actual numerical quantity, and this is the number that we're interested in. And this thing is a unit. Now, this unit doesn't have a direction attached to it, right? Degrees Celsius isn't pointing in some direction. I can't say that it's minus 10 degrees Celsius north. That doesn't make any sense. I mean, sure, the farther north you go, the colder it gets. But if I'm just talking about the temperature, it doesn't change. Like the temperature where I'm standing doesn't change if I turn around, right? If I'm facing north and it's minus 10 degrees where I am, if I turn around and I face south, it's still minus 10 degrees where I am. So uh, so temperature is an example of something that doesn't care about direction, so it's a scalar, but it has units. It has this stuff attached to the number. So another example of a scalar could be something like a distance. So something like 3 meters. Now, 3 meters is just a distance, right? So if I say that my, I don't know, if I say that my bookshelf is 3 meters tall, which it's totally not. It's like a meter and a bit. But if I said that my bookshelf was 3 meters tall, there's no direction that's really assigned to that, because you could maybe argue that, like, oh well, that's your direction that you're talking about is going upwards, from the ground upwards. Yeah, sure, but if I take the bookshelf, so if I've got my bookshelf, let me draw this here. So if I've got my bookshelf like this, and if we've got our shelves in here, and I say that it's 3 meters tall this way, well, then I could just take that same bookshelf and I could just tip it over. I could lay it on its side, right, so that it looks like this. And while I might not use the word tall, because it doesn't really make sense to talk about something being tall if you're going left to right, this direction, whether I say the word tall or not, this direction here is still 3 meters. This length in between here and here is still 3 meters, just the same as it was before. This here to here is 3 meters. So this quantity, this distance, this length, doesn't care about what direction I'm pointing in. Now, it makes a difference if I say that my neighbor's car is 10 meters west of my car, because now I'm attaching a direction of west, right? I could just, I could use something else. I could say my neighbor's car across the street is 10 meters north of mine. So I could put in whatever direction I want here, but this part, saying that something is some number of meters, I said 10 meters, but whatever, let's say let's make it 10 meters. So if I say my neighbor's car is 10 meters west of my car, now this thing is including a direction, right? It makes a difference if I'm talking about something to the left of my house or to the right of my house, because the neighbor on the other side, their car might not be 10 meters away. So I can't, I have to stick that direction onto it, right? If I say that my walk to school takes 30 minutes, time doesn't care about direction, right? I could say my walk to school is 30 minutes, but I could say that my school is whatever, 2.5 kilometers north of my house, and then I'm attaching that distance to it. And so sorry, not that distance, I'm attaching that direction to that distance, and that gives us an example of a vector quantity. And we're going to see some of these in a second. So just to go over the rest of what's on this slide, so we've said this first point, and we sort of looked at this third point, that numbers that have no direction are called scalars. So scalars, they don't have a direction, right? If you look at this second point here, scalars don't have a direction, but they do have a magnitude. They're a number with some size, how big the number is, right? But they don't have a direction attached to them. They can have other units attached to them, like this temperature right here is a scalar because it doesn't have a direction, but it does still have these units right there. So we're going to look in the rest of this lesson, we're going to look at the differences between vector quantities and scalar quantities, and just sort of, getting used to them. So here are some examples of scalars versus vectors. So scalars, as we talked about on the last slide, are numbers that don't need anything else attached to them to talk about something that you're seeing in the real world. Now, what I mean by only need a number right here is that they don't need a direction. They can still need units. So for example, most things that you'll use in physics have these units attached to them. So for example, temperature will be measured in degrees Celsius or degrees Fahrenheit or Kelvin. Now, just a little fun fact, it's not degrees Kelvin, it's just Kelvin. But those are examples of units that are attached to temperature. Distance also has units, and you can measure distances in things like meters or maybe kilometers, or if you're more comfortable with the imperial system, feet or miles or yards or whatever, right? Those are all examples of distances, and this is terrible. Let's try that again. Kilometers. There we go. Something like that. Yeah. So those are examples of units of distance. So they'll have these units attached to them because I can't say that somebody is 3 away from me, right? I have to say they're 3 something away from me. They could be 3 meters, in which case I'm standing pretty much just across from them, or they could be 3 kilometers away from me, which means they're somewhere else in the city. Or, you know, if I went into larger, more obscure units, then they could be several cities away from me. Right? So you need those units attached to it, right? Even if I'm talking about something like time, so time we're quite familiar with, we'll measure it in seconds, or we'll measure it in minutes, or we'll measure it in hours, or whatever, right? You could measure time in days. That's fine as a unit, but I can't say that I'll be there in 2. Right now, of course, if you're talking to somebody and you're in the middle of a conversation, then yeah, you can drop saying the units if you think the other person will understand. But if I'm just saying, hey, can you meet me in 2? I need to say 2 minutes or 2 hours or 2 days or 2 months, right? Because I need to give some more information besides just the number. But the important thing is that none of these things up here require a direction for you to talk about them. You might need some more complicated units. Just to finish this off, we got mass could be measured in something like grams or maybe kilograms. And just so that I don't run out of room, I'm not going to write any more than that. Speeds can get a little bit more complicated because you have to combine different units. So speed could be in something like meters per second or maybe kilometers per hour, something like that. So kilometers per hour is something that's pretty standard that you'll see lots like in society. Meters per second, you won't see it as much like on roads and stuff, but it's what we tend to use in physics. And actually, now that I think about it, maybe before we really dive into the rest of our unit, maybe I should make a sort of little mini lesson on units and how they work and why some units are special and things like that. So I'll see about that. So now that sort of covers scalar quantities. Now vector quantities are things that need a number, or a magnitude, and they need a direction. So examples of those are things that you don't see quite as much in day-to-day life as things like speeds and distances, but they are related. So for example, a velocity is just a speed with a direction attached to it. So you could also measure a velocity in kilometers per hour, for instance, but then you need to stick a direction onto it. So if I'm driving at a speed of 50 kilometers per hour, right, I could say I'm driving at a speed, or maybe a highway sign, or maybe not a highway, that's a really low speed for a highway, but a road sign says that your maximum speed cannot exceed 50 kilometers per hour. But if I'm talking about a velocity, then I need to attach a direction to that. I could say I was driving at 50 kilometers per hour south, right? Southwards from my town or from my house or whatever. I'm driving at 50 kilometers per hour south. So that would attach a direction to the number and to these units. Acceleration, momentum, force, these things get into more of the um, deeper physics stuff that we're going to touch on. So I'm not going to go into detail on those now, but those are examples of other types of things that have directions attached to them for their full description. So we can simplify our lives a little bit with how we write down vectors, because I don't want to have to say something like 10 I don't want to have to say something like 10 kilometers per second or per hour, let's say. I don't want to say something like 10 kilometers per hour east and then write out the whole word east every single time I want to write that down. Maybe I want to write down just the letter E for east. So maybe I just want to say 10 kilometers per hour east and write it this way. So using just this part of it. Maybe I want to write it like that. So actually, I'm going to get to that in a little bit more detail later on, but this is an example which sort of illustrates that we don't want to write out full words every time, right? So I've given another example here on the slide itself. So we use a lot of math to represent lots of stuff that's going on in reality. So just as you saw on the previous slide, or the slide before that, I wrote when I was talking about moving west, I used a W. When I was talking about moving south, I used S. And this doesn't apply to just directions or just to vector quantities. If I want to talk about a distance, maybe I don't want to write the whole word for distance. Maybe I just want to write D for distance or T for time, right? So what we'll do in physics a lot of the time is we'll shorten the stuff that we're talking about into just a single letter, and then we use that letter to represent that quantity that we're talking about. So for example, if I'm talking about a speed, I can call it some letter, whatever letter I want, but I'm going to show you some of the common ones that we'll use. I can label it with some letter, and I just have to keep using that letter every time that I'm talking about that speed. So for example, this equation is Newton's second law that we talked about briefly in our last video. Force is equal to mass times acceleration. Now I don't want to write out all those words every single time I want to work on a problem that involves forces and masses and accelerations. So what we do is we call the force just F, we call the mass a small m, and we call the acceleration this small a. It's not anything that you guys will really have to worry about right now, but pay attention to uppercase and lowercase letters, because you could be doing a physics problem someday where you have one mass that you call m and a different mass that you call capital M. And so in a question like that, both of these are called M, but the fact that this one's a capital M means something different than that one being a little m. So if you're writing it with lowercase letters, keep writing it with lowercase letters. And if you start out your problem by writing it with an uppercase letter, keep using that uppercase letter. So for example, mass, oftentimes we'll write it with a small m. Acceleration, oftentimes we'll write it with a small a. And force, oftentimes we'll write it with a capital F. But now remember from the last slide, and maybe go back if you need to, I said that force and acceleration are vector quantities, but mass is a scalar quantity. So how can I tell by looking at this equation what's a vector and what's a scalar? So I'm going to show you the notation that we use for that. Now, before I get to that notation, I'm going to make our lives even simpler. when we're writing different quantities in math and physics, where we're representing them with letters and not with numbers, I don't really need to write this multiplication sign in the middle. We can sort of ignore that multiplication sign. So if I take my white thing, I can get rid of this multiplication sign here, and it doesn't change what's going on in the problem. It's still mass times acceleration. The reason we need to have that multiplication sign when we're working with numbers is that if I write a 1 and I want to multiply it by 2, I can't just smush those numbers together, then it'll look like a 12. So I have to put something in the middle to show that it's multiplication. But with letters, because we only use one letter per thing that we're talking about, if you see two letters together, it's not some new thing, it's just the two of them being multiplied together. So this is still the mass, and this is still the acceleration, and we've just ditched the little x that used to go between them. Now we have this new sort of condensed notation where instead of writing out the whole word force equals and then the whole word mass times the whole word acceleration, now we've reduced it to F equals ma. But this thing is a vector quantity, and this thing is a vector quantity, but this thing is a scalar quantity. So once again, just by looking at it right now, we have no idea of how we're supposed to tell those apart aside from the circles that I've drawn around them. And you're not supposed to draw circles around all your stuff all the time, and you're not supposed to, you don't have to use different colors all the time. I'm going to show you the notation now. I think it's on the next slide, that we use for this kind of stuff. So force and acceleration, as we've been talking about on the past couple of slides, they are vector quantities. And so the way that we show that is by using these little arrows that you can see in our equation here. There's a little arrow above the acceleration, and there's a little arrow above the force, and that's how we differentiate between a scalar quantity and a vector quantity. A scalar quantity has no arrow above it. A vector does. So a vector will have that little arrow sticking out on top, and pretty much always, I've never really seen anybody write the arrow pointing to the left, so the convention is that the arrow points to the right every time. So if you're talking about momentum, in physics momentum, we write the letter P, and you would write this arrow above it. Now, for me personally, I get a little bit lazy with it, so if I'm writing something like, well, let's use the same equation. So if I'm writing something like F equals ma, I'll write my F, and then I don't write the full arrow, I just kind of do this, and that's the same thing. So that's just a matter of, when you're handwriting and you're trying to get through a problem, you don't want to have to stop every second to draw a neat little perfect arrow. So if you can just put that sort of something that looks somewhat like an arrow on top of the letter, then that gets the idea across. So I use these sort of half arrow things where I don't worry about the bottom part of the arrow, like the bottom part of I don't worry about this part right here. But yeah, some sort of arrow above the letter will do the trick. And there are other ways to write down vectors. For example, a lot of times in textbooks and stuff, if you see a vector when people are typing stuff out, they won't put these arrows on the vectors. What they'll do is that they'll make all the vectors bold, and then they'll leave all the scalars normal. So they'll have like an F that looks like this. And that's supposed to mean that it's a vector. And then the M, for example, in comparison, would be normal. And then the A would again be bold, because acceleration is also a vector. So it would look something like this, typed out and printed in a textbook. So There are some different ways to write vectors. There are definitely ones that I haven't talked about here, but these are sort of the two most common ones that you might come across if you're doing any sort of reading or working through physics questions. So now let's look at some specific examples of differences between scalars and vectors that are talking about almost the same thing. So I touched on this a few minutes ago when we were talking about speeds and velocities, how a velocity is basically just a speed but with a direction attached to it. So there's sort of an even simpler case of that, and that's the case of distance versus displacement. So distance is just like a regular length. It could be as a description of a distance. So for example, how tall I am is a distance, right? It's a distance from the top of my head to the ground, basically, or not even to the ground, because then that gives us this idea of up and down. It's the distance from the top of my head to the bottom of my feet is a distance, right? So if I'm lying down, my height hasn't changed except for the teeny tiny, decompression of my spine and stuff. But basically, my height hasn't changed. The distance from the top of my head to the bottom of my feet doesn't change if I'm standing up, because that's totally what I look like. Actually, I got to give myself that little, there we go. Or if I'm lying down, my height doesn't change, right? I'm still as tall as I was, more or less, as when I was standing up. And it doesn't care if I'm vertical or lying down or pointed north or any of that. It doesn't need any sort of direction attached to it. So it just describes, so if you're talking about a distance that you've walked, all that distance cares about is how much ground you actually covered. How far did you go? In terms of like counting up the total, however many steps you took kind of thing, is an example of measuring a distance. Displacement is a little bit different. It only cares about how much the object that we're talking about, how much it's moved from the start of the time that you care about it to the end of the time that you care about it. So this is a little bit weird. This is one thing that separates vectors from scalars, is that suppose I walk 2 kilometers from, so let me draw this in here. So if I've got, here's my starting point. Let's say I walk 2 kilometers to school and then 2 kilometers back home from school. Now distance-wise, I walked 2 kilometers that way. That looks like a Z, but sorry. That looks like a Z anyway, but whatever. I walked 2 kilometers north and then I walked 2 kilometers south. So in total, I'd say I walked 2 kilometers in the morning, I walked 2 kilometers in the afternoon. That's a total of 4 kilometers. That's my distance. My displacement only cares about the start and the end. Now, if I only care about the time I went from home to school, then my displacement is 2 kilometers, and my distance is 2 kilometers, and my displacement is 2 kilometers to the north. And because we're talking about a direction, maybe we can chuck in that little arrow to indicate that we're talking about a direction with that end there. So my displacement going from home to school was 2 kilometers north. My distance was just 2 kilometers. Going from school back home in the afternoon, I walked this way, so my distance was still 2 kilometers. But my displacement is now 2 kilometers south. But if I care about the whole thing, if I care about how far did I go from when I got out of bed this morning to when I got back into bed this evening, well, my bed's in the same place. My bed hasn't moved. So my total displacement from the start of the day to the end of the day is actually 0. Even though I moved around a ton during the day. I went to school, I came home, maybe I went somewhere else, and maybe I played a football game, and then I came home, and maybe I went out for a walk, and then I came home. But if my starting point and my end point are the same, my displacement is 0. So that's sort of a weird thing that takes some getting used to between scalars and vectors, is that my distance could be many, 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 many kilometers, but if I come back to the same place that I started, then my displacement is 0. Um, so yeah, so displacement is something that requires um, definite starting point that you're talking about, a definite ending point and ending time, I guess, depending on what you're looking at, that you're talking about, and it also needs direction. So as you saw with the school thing, my distance going from home to school is 2 kilometers, but my displacement going from home to school is 2 kilometers north. And then coming back home, my distance is 2 kilometers, but my displacement is 2 kilometers south. So displacement always has that direction attached to it. Um, and there are lots of different letters that you might see people use when they're talking about distances and displacements. They actually use the same. So like if you're using a D for distance, you'll also use a D for displacement, but you'll stick that arrow on top of it to show that it's a vector quantity. So sometimes you'll see D, and then if you pursue physics in like a university program, you'll see X and S used more often than D, because we end up using D for other stuff, calculus stuff that we're not interested in at this point in time. So here's sort of a visual way to look at distance and displacement and how they're different, is that here is our starting point. I'll put an S for start, and then here's our ending point. I'll put an E for end. And so you might have walked, this way, and then you turned here, and then you went, and then you maybe you wanted to go this way, but you had to turn left for some reason, so you went that way. You went all the way around here, and then you got to your end point at your friend's house or whatever, and your whole distance is that long, right? Is that whole blue line there, and it cares about things like if you need to take a different route, your distance will change, right? If I found a shortcut that'll take me from here to here in a straight line, then my distance would have gotten shorter than going all the way around. But my displacement only cares about where I started and where I ended. It doesn't care about anything else in the middle. It doesn't care if I took a detour or found a shortcut or if there was construction in the way or whatever. All it cares about is where did I start, where did I end, where's my point A, point B that I'm trying to walk to. And so that's the difference between distance and displacement. And displacement can paint that full picture by attaching a direction to it. So if I get rid of some of these lines and stuff that are on the screen, so I could say that suppose north is straight up in this picture, right? So if I've got north straight up in this picture, so then I could draw in like a little grid from my starting point, and then my grid looks something like this. So then that means north is up here, and that means south is over here, and west is over there, and east is over there, right? So now I'm seeing that this is getting confusing with our starting and ending point labels. So I'm going to call those points A and B. So we start at point A, and we end at point B. And I could say that this distance, whatever, I can measure that distance one way or another. But the direction, I could say, well, I was almost walking east. East would have been if I walked this way. But there was also a little portion of it where I had to go south, right? If you look at this blue line, I was basically walking east this whole time. And then I had to walk south. And then I had to backtrack a little bit, but we can ignore that. So if you look at the green displacement arrow, basically I walked mostly east, but then I also walked a little bit south. And so let's say that if I drew this, if I made a triangle out of this, so let me make draw in a proper triangle. So if I had a triangle like this, taking how far I went east up here and how far I went south down the side over there, then I can say that, well, if I've got a triangle, if I just redraw that same triangle out here, something like this, then I can figure out the angle that's in here, and I can use that to describe the direction of my displacement. So I could say, well, I was basically walking east, but then I also had to walk a little bit south, and where this was pointing, if this angle is like, let's say it's 30 degrees, then I could say I was walking east 30 degrees south, something like that. So then I could say my displacement was whatever, let's say 200 meters. 200 meters. So we've got our number and we've got our units. And now we need the direction. And then I could say, well, it was basically east, but if you look at that green arrow, there's a bit of an angle that goes south. So I can say east 30 degrees south. Something like that. So don't stress too much about, oh, what does this mean and how do I write all of this stuff? This is stuff we can talk about in our Zoom call, and I'll explain how this stuff works in greater detail. I'm just trying to get you guys to get a feel for how this stuff works. And as we talked about just a moment ago, there's a difference in how we write distances and displacements, and it's just including that little arrow on top of the letter. So usually you'll find that if you're writing a D for distance, you'll also write a D for displacement, but you'll use that arrow on top of it. So you won't come across someone that'll write, oh, well, I'm going to call my distance X, but I'm going to call my displacement S with the arrow. Chances are, if they've called their distance X, then their displacement is also the same thing, right? Or if they've called their distance S, then the displacement is the same thing, just with the arrow. So similar to distance and displacement, displacement is just distance but with a direction attached to it. Speed and velocity basically work the same way. Speed, in terms of like as a concept, like what is speed? Speed describes the distance that you've traveled. So let's say the distance d that you've traveled in a period of time t. So how many meters did you go in how many seconds is basically what a speed will tell you, or how many kilometers did you go in how many hours. And if you know both of those numbers, if you know that you traveled 400 kilometers in 4 hours, then you can calculate your speed to be 100 kilometers per hour. Now, it's a little bit confusing, but we write down speeds with a V instead of something like an S. And the reason for that, I mean, I don't know for sure if it's the reason for that, but I would guess that it's because we use V for velocity, and speed is very, very similar to velocity. So speed, if we write speed with a V, distance with a D, and time with a T, then we can say that speed is the distance that you traveled divided by how long it took you to travel that distance. That's your speed. And velocity is really similar, but instead of using distance, it uses displacement. So we have d with the little arrow there, and instead of speed, we have a velocity, so it also gets an arrow. And the time t is a scalar, so it's just a number, there's no direction attached to it. But also it's worth noting that you can't actually divide by a vector. And we're not going to worry about that point too much, but basically you should never have a vector by itself in the denominator of a fraction, because you can't divide by a vector. But yeah, so velocity is really similar, but because it's talking about displacement, remember that displacement had that really weird, it only cares about the start and end thing. So velocity works the same way. Velocity cares about the total displacement that you've covered. So if here's point A, hang on, let me draw that in. Here's point A, we'll call that point A, that's where you started, that's your house or whatever. And then here's point B, it's your friend's house. And suppose you traveled along this route, you go here, and then you go there, and then you go over here, and then you come and you end up at your friend's house. And that's the route that you took. Maybe you biked there and you wanted to see some scenery while you were at it. So that's your distance. That's your total distance, and if you take that total distance and you divide it by how long it took for you to cover that whole route, that'll give you the average speed that you were traveling at for that entire time. But your displacement is just a straight line pointing from A to B. And I'm going to put a little arrow there so that we remember that a displacement has a direction included with it. And so even though your route was this super long thing, maybe that took you 2 hours to cover like a really short distance, your displacement only cares that your starting point and your ending point were whatever, 200 meters apart. So if your displacement is 200 meters, we'll simplify this and we'll say it's in, we'll use the same, now we'll simplify it. We'll pretend that this is perfectly horizontal and we'll say that it's 200 meters to the east. You'll say that your friend's house is 200 meters to the east of your house. So that could be your displacement, but to get your velocity, you have to divide it by the time it took for you to get there. So even if it's only a distance of 200 meters, if you took a really roundabout route to get there, maybe it took you a couple of hours to actually end up at your friend's house. So then you would get that your velocity v is your displacement, so that's 200 meters. And let's say it took you 2 hours. And you're traveling to the east, and this east is attached to your displacement up there. So then you can do that calculation, and if you just do a little bit of math, you get that with 200 divided by 2, that's 100. So I'm going to have to write this down here and in a darker color. So you'll get an answer of 100 meters per hour east. And so that would be your velocity. So that's kind of how this works. It's similar to the way speed works, but it also has that weird start point, end point thing that displacement has attached to it. So the math that you do works out exactly the same way that your speed would, right? Suppose it took you 2 hours, so you could calculate your speed and you can show that it's different from your velocity. Suppose the route that you took was actually 2 kilometers, right? And 2 kilometers is 2,000 meters. Right? And it took you 2 hours, right? The time is the same, going from the same point A to point B, so it still took you 2 hours. And if you do that calculation, then you'll get that it was 1,000 meters, that you covered 1,000 meters per hour. But you could write hours as H or HR, whatever, or HRS. So you can see that your speed, whoops, you can see that your speed right here and your velocity down here are not the same. And that's because the speed cares about the distance, but the velocity cares about the displacement. Now, the next thing that we're going to talk about is acceleration. And acceleration is similar to the connection between speed and distance, or actually maybe even better than that. It's similar to the connection between velocity and displacement in that you take one of these vectors, you divide it by the time, and you get a new quantity. So if you remember from the last slide, we had our velocity is equal to our displacement over time. So acceleration has a really similar structure to that. The acceleration is just the velocity divided by the time. And so it basically describes how an object's velocity changes over time. And you might see this if you look in a book. This version of the equation depends on you starting your stopwatch at 0 seconds and starting your velocity from 0 speed, so from rest. So your velocity at the time that you start your timer, your velocity is 0, and then you let your stopwatch run and you speed up, and then you measure your speed at the end, and that gives you your average acceleration. You might see acceleration written in a textbook like this, with this triangle, and with another triangle down here. And we're going to talk about this more next lesson, but that triangle basically just means the change in whatever quantity is beside it. So down here, this means the change in your time. So the difference between your start time and your end time. And up here, this means the change in your velocity. So the difference between your starting velocity and your ending velocity. So it looks a little bit more complicated than this, but I'm just trying to give you guys a basic idea of how the stuff works and how the stuff is connected to each other. And of course, because acceleration depends on the velocity has a direction attached to it, and you're not allowed to just chuck that direction out the window. So the acceleration keeps that direction attached to it, and therefore it's also a vector quantity. And so that's why you got the little arrow above the A there. And of course, the last thing on the slide is that we use the letter A to describe acceleration. So now I just said that you can't chuck the direction out the window, but maybe you don't care about the direction in every question that you do. Now, mathematically speaking, you can't just chuck the direction out the window, but if you're getting to the point of, well, my final answer only cares about, it doesn't care about the direction. So for example, if we're talking about acceleration, which is how quickly or how slowly you speed up or slow down, then maybe I don't care about what direction I was moving in when I was speeding up. I just care about how fast I was speeding up. So then I could take the magnitude of my acceleration, right? If I've got an acceleration of well, I don't want to use acceleration because the units are a little bit weird, but I'll use acceleration anyway. So acceleration is how quickly you change your speed per unit of time. So let's say I had an acceleration of, so I'm going to write out the units and then I'm going to explain it. So suppose it was 3 meters per second. And what that means is that my velocity changed. So remember, velocity is just like speed, and speed is a distance over a time, or a distance divided by a time. So this right here is a speed, right? This right here is a speed. So I'm saying that my acceleration is that my speed increased by 3 meters per second every second. And that's what this extra S down here is for. Don't worry about if you're not understanding the units, but notice that in what I've done right here, I haven't included the direction. Maybe I don't care, for whatever reason, I don't care about the direction I was moving in while I was speeding up. All that I care about is that I was speeding up at that speed, or at that rate. So I put these two lines around my A for acceleration, and this is the magnitude of the acceleration. So remember that scalars, so those are numbers that don't have a direction, they only have a magnitude. So you can say that your scalar is made up of two parts, right? A magnitude, your scalar is made up of one part, which is just a magnitude. Your vector is made up of two parts, which is a magnitude and a direction. So if you're just looking at the magnitude of your vector, let me write this down a little bit in the corner. So your scalar is just magnitude, right? Your vector is a magnitude plus a direction, right? It's a magnitude and then it's got a direction attached to it. So a magnitude plus a direction. So the magnitude of the vector basically just ignores the direction. You just forget about this part, and you're only looking at how big this is. And as we saw in our speed and velocity example, they're not always going to be the same number, right? So it's going to be different from your regular distance, for example, if you're talking about displacement. So I've got an example here on the screen which you can read through, and I'll read through it with you. We'll draw a little picture so that you can hopefully understand this idea a little bit better. So suppose you start from your house. We'll say east is to the right in our little diagram down here. So I'll make a little note here that east is to the right. Cool? So suppose here's your house, that's point A. And then let's say you walk to your friend's house. So you walk 5 kilometers east. So you walk up to your friend's house here, that's point B. And then you walk to an ice cream truck or an ice cream stand or colmado or something here at point C, which is west of your friend's house but east of your house, right? It's in between your two houses. So if you walk from point A to point B, that's 5 kilometers. So your distance between your house and your friend's house is 5 kilometers. Your displacement when you walk to their house is 5 kilometers east. And then suppose you walked 5 kilometers east to your friend's house, and then you walked 3 kilometers west towards the colmado to get your ice cream or something like that. And you walk 3 kilometers that way. So your total distance is, well, you walked 5 kilometers from your house to your friend's house, and then you walked 3 kilometers backtracking towards your house, but your total distance is 8 kilometers, right? Your total distance is the distance to your friend's house, and then the distance from your friend's house to the ice cream. But your displacement only cares about where you started, which is here, and where you ended, which was here. And this distance in here is only 2 kilometers. So your displacement starting from point A and then going towards point C, because that's where you ended up, is 2 kilometers east. So we need to include the east for the direction. But if I only care about the displacement, then I can drop the east part. If I only care about the magnitude of the displacement, then I can drop the east part and say it's just 2 kilometers, which you can see is different from just talking about the distance. So even though the magnitude of the displacement doesn't have a direction attached to it, it's still not the same thing as your distance. So mathematically speaking, I sort of showed you this a little bit on the last slide. The way that we'll write down, so we'll write down a scalar, so like your speed would be the letter v, your velocity would be the letter v with an arrow, and the magnitude of your velocity, well, since we're talking about a velocity, we have to write down the arrow, but then the magnitude means that we add these two bars, one to either side. And so that's how you would represent the magnitude, is this one, is the magnitude of a vector. Now, with speed and velocity, it can get a little bit messy because the speed isn't necessarily equal to the velocity. So we need to write down the magnitude of the velocity in this kind of complicated way so that we don't confuse it with our speed v. But in some cases, like when we're talking about acceleration, if the only symbol that uses the letter A in the question is your acceleration, then while this is how you should write the magnitude of the acceleration, if there's nothing else going on, you could basically just write it like this, because since you're talking about the magnitude, that means you're not including a direction, which means it doesn't need the arrow anymore. But you also don't need to write it this super complicated way because there's nothing else that you could confuse that value with, right? If I'm talking about a speed v, if I'm talking about a speed v and a magnitude of a velocity, and I write them the same way, it's confusing to keep track of which is which. So I'll write the magnitude of my velocity like this, and I'll write the speed like this. But for acceleration, if it's the only thing that has the letter A in the problem, then I can write my magnitude of my acceleration like this, or I can write it as just a lowercase a without anything attached to it, because there's nothing else that a could possibly mean. So I know there's a lot going on in this lesson. don't stress too much about understanding all of this on the first run through. It's just a matter of I want to expose you to what some of this stuff looks like, and then we can talk about it later on. So when it comes to describing how things move, if you remember last lesson we talked about our introduction to motion, we use a lot of math to describe how things move. We can use math to describe where a position, where an object is located, so that's its position. Then we can talk about its displacement, which is how it moves over time with a direction attached to it. So if it starts here, we can talk about how it ended up over time, it moved to here. So that's its displacement. And then the velocity cares about how long it took for you to get from point A to point B. So the displacement is how far that distance is, and the velocity cares about how quickly you covered that distance, and when you attach the direction to it, how quickly you covered that displacement. And then acceleration cares about how the velocity changed. So if you started out at a standstill at your house, and then you were walking here and here and here, and you're walking slowly, and then you speed up and you start jogging here, and then you start sprinting by the time you get to the end, well, here your velocity is really small, right? Because you're just at a leisurely, slow-paced walk. Here your velocity is bigger because you started jogging, and then here you're full-on running, so your velocity is much, much bigger, and your acceleration cares about this change in your velocity. And so those things help us describe how things move. That's basically it for this lesson. We've talked about how we've talked about what vectors are. We've talked about how they're different from scalars. We've talked about different types of scalars. So we talked about things like distances and a little bit of mass and time and temperature. We talked about some vectors, so displacement, velocity, and acceleration. And that's kind of all that I wanted to cover. This is how we describe motion. This is some of the math that we use, things like that. So that's about it. I'm just going to go to the last slide because it's an intro to our next lesson. And yeah, so that's about it for today's video. I'll put out the next science lesson hopefully later this week, but possibly over the weekend or early next week. I know there was a lot of math that was sort of thrown at you, like there's just a whole bunch of letters and arrows and symbols that you're not used to seeing before. Don't worry about understanding all the math. I'm not going to test you on that math, and certainly I'm not going to test you on doing it from scratch. The most I would ask you to do on a test that involves the kind of math that we're doing is I would say, so speed is equal to distance over time, and I'd say that in words, and I'd say write down what that looks like mathematically. So all that you would need to remember is that speed is v, distance is d, and time is t, and write down v is equal to d over t. So the most I would ask you to remember is things like that, and maybe to remember things like how vectors have these arrows above them. So I could say speed is equal to distance over time, and velocity is equal to displacement over time. How do these equations look different? And maybe so that's the most I would ask you to do. I'm not going to say, okay, so starting from Newton's second law, show me that this is this. I'm not going to do any of that weird kind of stuff. That's more complicated than I'm interested in us going into. A fair warning, the next lesson that we do is also kind of math heavy because, well, the whole lesson is about 4 equations. So we're going to be building up to looking at those equations, looking at what they mean. Now I do say that this is the next lesson, but literally while recording this one, I've thought that maybe I should make a lesson that's sort of like a lesson 2.5 that talks about units and how they work and why they're important. So possibly I will do that, but possibly I will skip over it and we'll just talk about units in our Zoom session. But either way, the next video should hopefully be out later this week or early next week. My classes are kind of extra heavy this semester, so I'm sorry if there are delays like there were last term. But But I'm looking forward to it, and I hope you guys are not feeling too intimidated by what we've talked about today. As always, if you have any questions whatsoever about any of the stuff in this lesson, send me an email, hit me up in the Google Classroom, leave a comment. But that's about it, and I will see you all in the next video. Have a good one.